Okay, everyone, as promised, here is your next killer video for AP Physics 1. We're going to work through the problems we didn't quite get to today, didn't quite get to review today, 12 through 16 on Unit 4's multiple choice questions, Part A. Okay, so here's number 12, and I'm going to read it quickly. I'm really going to try to keep these under 2 minutes each to keep the video short. And so let's be quick about this. A rock of a given mass is thrown from the edge of a cliff with an initial velocity at an angle of theta, as shown above. Point P is the highest point in its trajectory, and Q is level with the initial position of the rock. All frictional forces are negligible. Which of the following correctly describes the total energy of the rock-Earth system at points P and Q? Okay, well that's kind of funny, because on this one I guess what that means is we have to watch our P's and Q's here. All right, so everybody, watch your manners. Keep it polite. We're gonna watch our P's and Q's here. I don't know. So the rock Earth system, is that what I just read? The rock Earth system. So and all other forces are negligible. So that we got a rock, and the only force on it is gravity. So this is a closed system, right? And I'm going to switch to my desk camera here. And what I'm going to do is simply this. I'm going to say to myself, "Hey, you, self. What kind of energy does the rock have up here?" Well, let's see. It's up high, but it's also going some speed that way, right? It's got velocity on the x-axis here. Even though it's not moving on the y-axis, it's got x-axis velocity. So up here, it's got both PE and KE. Okay, and then at Q, I don't know, same thing. It's off the ground some height h. It's off the ground some height, and and it's going this way. So it's got a lot of velocity, it's got more velocity, but it's still got height. So it's got U plus K here. It's got potential energy and kinetic energy here too. And this quantity is the same as this quantity. Right? This one up here has more potential energy, it's up higher, but it's going slower, so it's got less kinetic energy. And when it falls to this position, it's got less potential energy, but it's got more kinetic energy because it's speeding up. And the reason I know they're equal to each other is because it's a closed system. The only force on that rock is the gravity force. There's no birds or bees pushing on it. There's no little, there's no air friction. It mentions that, right? So I'm going to just go ahead and say the energy before is equal to the energy after. I'm looking for a statement that's U plus K. I don't know, mgy or mgh plus 1/2 mv squared is a constant. Is the same as the same as it after the fact. All right, so let's go find our answer. At point P, what am I looking at here? Which of the following correctly describes the total energies? At point P, it's got no energy. No, of course not. It's got plenty of energy up there. Right? It's got plenty of energy up there. The total energy. At point P, does it have any energy? Yes, it does. A is not our answer. At point P, it's got MGH. Well, that's true, it's got MGH, but it's also moving sideways, so be careful. It does have MGH, but it's also got KE, right? So that's not quite right. Well, look at this one. Here's the answer, C. That's the answer, right? Because at point P, what does it have? At point P, it's got potential energy and kinetic energy at point P. And what does it have at point Q? Well, it's got potential energy and kinetic energy at point Q also. It's got PE here and KE. It's got PE here and KE, or in our updated lingo, it's got U, stored energy, potential energy, and kinetic energy at both positions. Right. So the answer here is definitely C. Indeed. Moving on. The next question is a ball of mass m rotating on a string, and it moves clockwise in a vertical circle as shown above. So it's going this way, clockwise. It's going this way. Which of the following is true about the ball string Earth system? Okay, so we've got a ball, we've got the string, we've got the Earth, as it moves from point 1 to point 2. As it moves from point 1 to point 2. Well, as it moves from point 1 to point 2, okay, so up up here, it's got, when it's at this point, it's got, it's moving. So it's got potential energy and kinetic energy in both positions. Well, let's call this 0. We'll call this 0. So let's call that 0 meters. I don't think we have a number for R. We just have R, right? Let me double check that. We might have a number. No, that's okay. So up here, the ball is higher, right? How much higher? So height, do you agree with me? The height up here is 2R, right? 1R, 2R. The height is 2R. So the height is 2R. Okay. So I think it just said, what's the potential energy change? Is that what I just read? Which of the following is true about this? Okay, which of the following is true? The PE, potential energy decreases by mgr, and the tension increases by some amount. Well, wait, that's not true. That's not true. It can't be true, because look, the PE doesn't decrease by mgr, it increases by twice that. Right? Because PE, gravitational, is mg times height, or mgy, or mgh. But h is 2r. So if it went from here to here, well, then up here it would have had a quantity of the height would be 2r times m times g. So the gravity change is m times g times 2r. 2r is the height. So the change in potential energy, is going to be twice mgr, not just mgr, because r is only half the distance it falls, right? So let's go find one that has a change in potential energy of 2 mgr, and take it from there. Okay, so I don't like A, because it's just mgr. And look at B. I don't like B. It's just mgr. Oh, C looks reasonable. Let's see, 2 mgr. Okay, so it's either C or D. So again, we seem to be doing this a lot today, especially. We're able to throw 2 in the trash really quickly here, right? Just by being clear about our setup. Right, so it's definitely C or D. Let's see what else is factored in here. The tension in the string increases by twice its weight when it goes down, because it's going faster and faster, right? And the tension increases by more than twice its weight. Oh, I can tell you now, it's going to be this one. It's going to be D, but let's try to prove it. It's going to be D, because, let's go back to my camera. Okay, so the tension in the string, well, don't forget, the force required to keep something going in a circle, this is why I was so quick to choose it. The force required to keep something going in a circle is m times a, where a is v squared over r. Right? So when the ball is down here at position 2, there's got to be a tension in the string to keep it going that way, to keep it going in a circle, right? But there's weight on it, right? So at a very minimum, it's going to be more than the weight, because if the ball was just hanging by the string and not moving, then the force down on it would be m times g, right? Be m times g. So it's going to be more than that. It's going to be more than mg for sure, right? Sorry, if it's just hanging from a string, it would be mg. Let me go back to my options here. I forget what my options are. Twice mg and more than twice mg. I still think it's more than twice mg. Let's see if we can work that out. That's my intuition. Let's go with it. Let's see what we get here. So what happens here? Well, the ball ends up having kinetic energy, more kinetic energy than at the top. So that if the potential energy went here, the potential energy went down by that much, right? It fell from here to here. And so the potential energy change was equal to mgh, which is 2 mg times r, right? So if that's the change, if that's the amount of potential energy that was lost, and it's a closed system, which it is, then that's the amount the kinetic energy went up. So the increase in kinetic energy, the delta K, the change in kinetic energy, is equal to 2 mgr. And so that means that the change in kinetic energy, the energy went up. It already had some, but the energy went up. The change in kinetic energy is equal to 1/2 mv squared is equal to 2mgr. Let's see if this gets us anywhere here. Yeah, I think it should. All right, so let's just say this. Let's say, gosh, I don't know. Let's multiply both sides by 2. I see fractions and I try to get rid of them. Right, so multiply by 2. And let's divide by m while we're at it. Right? So I get v squared multiplied by 2 is 4gr. So its velocity down at the bottom will have increased by, it already had some velocity, but the velocity, so I really should be writing delta v. The v will have increased by, well, take the square root, right? Square root of 4 is 2, and the square root of g times r is the square root of whatever, g times r. So the change in velocity is going up by 2 times the square root of g times r. Well, g is 10. We don't know what radius is, so let's see if this gets us anywhere. But the change in velocity goes up by 2gr, and so the force, what happens to the force? Well, it goes up. Yeah, look at this. So I'm going to switch colors here so it's easy to follow. So the force is mv. The force goes up by this amount. The force goes up by mv squared over r. Well, there's v. V squared. Let's see. 2 squared is 4. Root of g times r squared is g times r. Mv squared over r. So r's cancel. The force goes up by 4 mg, by 4 times its weight. That's how much it goes up by. And we don't know what it was at the top, but it was a non-zero value up there too, the tension, right? The velocity and the force on it, right? So it's even higher than 4 mg. It's even higher. It's even higher than 4 times its weight. It's probably 5 or 6 times its weight, but we don't have to work that out because we just have to know if it's more than twice, and it is certainly more than twice its weight. Right? The increase in the force and the tension. Right? So let's go find that one. So it's definitely this or this. Decreases by 2 mgr. Tension in the string increases by twice the weight. No, it's more than that. Increased by more than twice the weight. Yes. So this one is definitely D. I'm saying definitely a lot. I sure hope I'm right. No, I'm right. I have to be. Yes, phew. Okay. 14. Try to speed up here a little bit. 14. Let's see what's going on here. A small block of a given mass is released from a rest at a given height. Oh, look, we're going to have to do some calculations here. If you see numbers, you're going to have to calculate, generally. Above the bottom of a track, it slides down the track and inside the loop. The speed of the block is 2.5 meters a second at point 3. Which of the following about the situation is correct? Let's see what we're after here. Gravitational potential energy, block Earth system at point 3 is less than 0.2. No. The PE is less at 3 than 2. No, the PE is more at 3 than 2. A is not our answer. I don't like it. The K of the block at 3 is greater than the K of the block at 2. The K of the block at 3 is greater. No, definitely not. It's definitely not B. I'm not even doing any calculations. I'm not really doing much yet. I'm just looking for some that I can throw in the trash. And I'm throwing A and B in the trash real quickly because the KE is the energy of motion. So at 3 is greater than 2, that means it's going faster here than here. If this cart, or whatever this thing is, rolls down here, it's not going to speed up between 2 and 3. It's going to slow down between 2 and 3. So without really doing any physics, formally at all yet, I've got A and B in the trash. Again, we're at a flip of a coin. C and D. These are going to be more complicated. Let's see. The mechanical energy of the system at 3 is less than the mechanical energy of the block at 1. Well, it should be the same if there's no friction. Does it say that? No, it doesn't say that. We don't know. Is equal to. Oh, I see. Yeah. So at point 2. So mechanical energy at point 2 is equal to the gravitational PE at point 1. Well, that could be true if there's no friction. That would be true if there's no friction, but we don't know that. I bet it's C, but let's work it out. I bet it's C. My intuition, without doing any physics, is that it's C. Let's work this out, though. What do we know? So let's switch to my camera. So I wrote down what we know. Here it is. I'll go up a little higher so you can see the picture and the work I do. Try to be quick about this. So I guess what we're after here is I'm really wondering, so if there's no friction, D is our answer. If there is friction, C is our answer. Do you understand? Mechanical energy of the system at 2 is equal to the potential energy of the blocker system at 1, because up here it's released from rest. So up here it has PE, and it's not moving. It's just got PE. So the total energy in the system here is just PE. And if there's no friction, then the total mechanical energy here, the total mechanical energy everywhere is the same if there's no friction. So D is correct if there's no friction, but I don't know that's true. It doesn't say that here. I bet the answer is C. If I was in a rush, I would choose C and I'd keep going, but I'm not. So I'm gonna work it out. So at point 3. So let's find out how fast it should be going at point 3, because look, the speed is 2.5. So let's figure out how fast it should be going. And if it should be going 2.5, then there's no friction. And D's our answer. Right? But if it should be going faster than 2.5 at 3, then C's our answer. It lost some energy. Okay, so let's work it out. Let's see here. What's R? R is 0.6 meters. Yeah, okay, so we can do this. There's a quick way and there's a quicker way. Let's do the quicker way. Okay. Basically speaking, remember the path doesn't matter. We're wondering about the thing here versus the thing at point 3. And R is 0.6 meters. What's H? 1.8 meters, right? So this is 0.6 meters. This is another 0.6 meters. So this is 1.2 meters high. Right, from the bottom here, from this reference point. That's an M, sorry. So the ball is, or the track, or the cart, or whatever the thing is, the cart is 1.2 meters high here, and it started from 1.8 meters. So it fell, basically, it's, remember the path doesn't matter. It went from this energy level to that energy level. And the path doesn't matter if there's no friction, which is what we're checking, right? So let's see if there's no friction. Because if so, if there's no friction, we're going to get 2.5 for the energy change. Right? Up here, it had all gravitational potential energy. Up here, we're checking, does it have just kinetic energy, or did it get robbed by friction? Well, this is the same thing as falling. Right? This is the same thing as falling 1.8 minus 1.2. This point is 0.6 meters. That's 0.6 meters. Basically, this thing fell 0.6 meters. Basically, this thing went from here to here, okay? And if there's no energy loss, the velocity will be 2.5, according to our calculations. Now let's calculate. What should the energy be? Well, if something falls 0.6 meters, how fast should it be going? Well, the potential energy turns into the kinetic energy. The mgy, mgh, I use those interchangeably, I hope that's okay. The mgy turned into 1/2 mv squared, multiplied by 2, divide by m. The mass didn't change. So I get 2gy divided by m is v squared. Velocity is root 2gy. Root 2g, 0.6 meters. 0.6 meters. And so 20 times 0.6 is 12, and root 12 is more than 2.5. Right? It's more than 2.5. Root 12. I'm looking for root 12. Did I do that right? I'm going to double check myself. I'll do the whole thing. 2 times 10 times 0.6. Root of that is 3.46. That ball, if there's no friction, that ball should be going about 3.46 meters per second. That ball should be if this is frictionless, if friction did not rob us, that ball is going 3.46. But it did, because look, they say it's only going 2.5. We got robbed. We got robbed of energy. So this isn't true because friction is present. The mechanical energy of the system at 3 is less than the energy of the system at 1. Yes, 3 is less than 1 because it's only going 2.5. It got robbed. It should be going 3.46, but it's not. It's missing energy here. It's going slower than we think it should be if there's no friction. So there is friction, and the friction heated up the ramp, and it heated up the wheels, and whatever else is rubbing against the stuff here, the bearings and all the rest, whatever's going on exactly. But As it rolled, it got robbed by friction and heat losses, and so thermal energy entered the system, and mechanical energy was lost, and that's why it's only going 2.5 here, not 3.5 meters a second. The answer here is undoubtedly C. Hey! Okay. 15. Oh, this one I didn't even draw because we're going to get it so quickly. Is that true? Yes, I did not draw this one. I don't even have a drawing for this because it's going to be so fast. This is an Atwood's machine where one weight is heavier than another weight, so it's going to accelerate downwards. They're connected by a string of negligible mass suspended vertically over a pulley, creating an Atwood's machine, as shown in the figure. The objects are initially at rest, and the mass of object Y is greater than object X. And as object Y falls, how does the KE of the center of mass change? The kinetic energy of the center of mass. Well, where is the center of mass of this system? It's always closer to object Y, right? Exactly where it is, I don't know, because we don't have the exact masses or the distances. If we did, we could calculate where the center of mass is. But we know it's closer to Y because Y is more massive. So where's the center of mass of the system? It's somewhere in this region up here. But as we let the weight fall, that center of mass is going to move with object Y. Object X is going to go up. And so the center of mass is going to go down. Let's see what happens here. What are we after here? How does the KE of the center of mass of the two object system change? Well, it's going to do what object Y does. It's going to accelerate. The KE is going to do what the object does. The KE is going to increase. Okay, let's see here. How are we doing? Well, okay, look at this. Again, 2 are in the trash. I don't like C, I don't like D, because it's speeding up. And the heavier object is speeding up. The center of mass is always closer to the heavier object. And so the center of mass is speeding up as the object speeds up. And so C and D are in the trash. I like my chances. I got a 50-50 chance here, but I'm going to do better than that. The KE increases, okay, because the gravitational force due to Earth does positive work on the system. Yes, that's it. Because when the force is in the direction of the motion, that's positive work. When the force is against the motion, that slows things down. That's called negative work. So this thing is accelerating downward in the direction of the force. The answer is A. It's not B. The answer is A. Indeed. And number 16. Okay, this one I drew. A small object of mass m is shot horizontally from a launcher that's attached to a table. Friction is negligible. The ball strikes the ground some distance from the base as shown above. And a second object with half the mass, m over 2, half the mass is launched from the same launcher such that the spring is compressed the same distance as in the original scenario. The distance from the base of the table is, okay. Well, I saw one I can throw in the trash without even thinking, which is B, right? Because if this spring gets compressed some distance and you shoot a ball, remember projectile motion? Whether you drop the ball or shoot it at 100 miles an hour horizontally, it still takes the same amount of time to hit the ground below, right? It doesn't wait because it's going fast or something like that. Wile E. Coyote he wasn't a very good physics student. When I drop an object, it takes the same amount of time. If I shoot it 100 miles an hour or 10 miles an hour, it takes the same amount of time to fall. Okay, so basically what I'm driving at here is if we find the ball is shot twice as fast, it's going to spend the same amount of time in the air no matter how fast it's going sideways. Right? So if it's going twice as fast for some time value, it's going to go twice as far. And if it's going 10 times faster, it's going to go 10 times farther. And if it's going half as fast, it's going to go half as far. Okay? Now, I was really fast to throw B in the trash because I know just from intuition, if I put a ball on a spring and I compress it and I shoot it, it goes some speed. And if I put a ball with half the mass on the same spring and I compress it in the same way, it's going to go faster. Right? Same push, same energy in the spring if you compress it the same distance, same delta E in the spring, right? Same energy transfer, but if it's got less mass, it's going to accelerate more rapidly. So it's going to be going faster. A ball with lesser mass is going to go faster. So it's going to go greater than D. It's not going to go D, it's going to go greater than D. A is in the trash too. Greater than half the distance, but less than D. No, it's going to be going faster. It's got less mass. It's going to be going faster. It's C or it's D. Again, 50-50, but let's do better than that, right? It's going to be a function of root 2, right? But so it's going to be root 2. It's going to be C. But let me prove that to you. It's going to be C. It's going to be a function of root 2, and I'll show you why. Right, so what's going on here is we've got energy in the spring, and then it turns into kinetic energy, right? So energy here is spring energy, U, elastic. The kinetic, then it turns into the energy here is kinetic energy, right? And so the elastic potential energy, the energy in the spring, is being used to accelerate a ball, giving it kinetic energy. Okay, I go to my equation sheet, I pull up some equations. 1/2 k times x squared is going to equal the kinetic energy 1/2 m times v squared. Well, let's simplify that. I see fractions, I don't like them. So I'm going to multiply both sides by 2. And I get k times x squared is equal to m times v squared. How will the velocities compare? Divide by m. V squared is kx squared over m, kx squared over m. Okay, so check this out. This is the same value for both balls, right? It's the same spring, and it got compressed the same distance. What's changing is the mass. So V, well, let's just write out the equation first, is going to equal the root of k times x squared over m, but that's just some value. So what's the proportionality? Well, V will be proportional to the root of 1 over m. Those two values are staying the same, so I'm just going to call that 1 to see what's happening. So what will the new velocity be? It'll be less than the first velocity by the square root of 1 over m, right? So the velocity is going to be m goes down, right? So it was say let's say with the first launch it's called the mass 1, right? So for the first launch the mass was 1, so the v would be proportional to root of 1 over 1. So let's just call it 1 unit of velocity for the first launch that got it to go distance d, right? So some velocity of a unit of 1. It's not actually meters per second. That's just like some reference point. What about the second velocity when we launch it with a lesser mass? Well, then it's going to be root. This is why I said that it's going to be a function of root 2, because the mass just got cut in half. The mass just got cut in half. So the new velocity is going to be, if the first velocity was 1, the second velocity is root 2. Right? 1 over 0.5 is 2. And root 2 is 1.4. So the velocity of the second launch is 1.4 times faster than the first launch. It's going faster on the second launch, but not by a factor of 2, by a factor of 1.4. So it's going to go 1.4 times farther. It's going to go 1.4 times farther than the first one did. No. Greater than D, but less than 2D. What did I say? 1.4. It's going to go 1.4D. C's our answer. C's our answer. Yes. Okay. Great. That's that. Sorry it took so long, but it's tricky stuff, and it's good to treat it slowly and methodically. And now go knock these down on the new. I'm going to make a new copy of this right about now, and go knock those down and have a great weekend. All right, guys. See you soon.